Hi, welcome to Nanotalks. This Nanotalk is a recording of our very first user webinar that we did with Dr. Marc-Georg Willinger, who talked about multi-scale in situ observation of catalyst dynamics under reactive conditions. This webinar was hosted by me, Olaf Weller, and at the end you will hear some questions from our climate product manager, Ronald Marks. The presenter of this user webinar was our climate user, Dr. Marc Willinger, who helped us back in 2016 at FHI Berlin with the development of our gas supply system. Currently, Marc Willinger is the group leader at the Scientific Center for Optical and Electron Microscopy at ETH Zürich, and also the group leader of the EM group at the Department of Inorganic Chemistry at FHI Berlin. The presentation of Marc lasts 40 minutes, and then you can listen to the Q&A session we held with the audience. I hope you enjoy this Nanotalk.
Hello everyone, I just switched to presenting mode, So I will speak about multi-scale in situ observation of catalyst dynamics under reactive conditions. So I don't know exactly who you all are, and so I start first quickly with a few words on catalysis. So catalysis is a quite complex multi-scale phenomena. You see that there are some processes happening on the very small scale, and like atomic and electronic excitements at very small time and lateral scales. But there are also processes that are involving actually larger scales, like catalytic reactors where heat and mass have to transport it. So it's really a multi-scale phenomena and not easy to understand. And we're trying to attack this problem with electron microscopy. Now, a word on electron microscopes. So the modern tools, the modern electron microscopes, the TEMs, are nearly perfect instruments. So we can see really individual atoms, atomic columns. We can, with spectroscopy methods, we can analyze what kind of atoms we have here, what kind of oxidation states even. And as you look at this picture, for example, I hope you can see my mouse, you see a particle. That's actually a catalyst for methanol synthesis. It's a copper particle on a zinc oxide support. You see here on the surface, there are some steps. There is a defect here, a twinning boundary. And when you look at this particle, trying to understand how the catalyst works, you look at the surface atoms and you see some of these atoms at steps are slightly under-coordinated. And you could imagine that these are sites where a catalytic reaction could happen. Now, there are two problems here. The first problem is that although we have all these details, it's not a representative state because a catalyst is normally not in vacuum. It's surrounded by gases and in some kind of temperature and gas condition. And then the next point is an electron microscope is the perfect tool to learn more and more about less and less. So you can know all the details about some single atoms. But that's like here on the right side, like you study all the features of one little piece. But in order to understand the whole, you need to look at the context in which it moves and in which it is embedded. And so that's about the two pitfalls of electron microscopy, the necessity of vacuum for good resolution and the huge amount of local information, but this sometimes miss a bit the context. Now, I have an example for context. We have in Berlin studied a simple model reaction here. This is a carrier of alumina, and on that cylindrical carrier, there is at one point in some region some platinum deposited. And through this catalyst bed, there was a hole was drilled, so we could actually in that system we could move a fiber through the catalyst bed and abstract with a hole the gas samples to a mass spectrometer, and we could also insert a fiber into spectroscopy along the catalyst bed. And the reaction that was studied was partial oxidation of methane. And here's a plot of what happens along the catalyst bed. So at the point where the catalyst starts, that's a position 0 here in the diagram on the right side. And you have incoming oxygen and methane. As soon as they reach the catalyst, the reaction starts. So the first platinum particles just down here, they see really the methane and the oxygen. But as you see, the concentration of methane and oxygen due to the total conversion changes very fast. In a few millimeters, there's basically no more oxygen. And you see lots of different adducts forming, and even they start to further react with each other. So what I want to point out here is that if someone gives you some sample that he abstracted or she abstracted from a catalyst reactor, and you go now and take a few particles, go to the TM and study all details, if you don't really know what kind of environment that particle has really seen in your reaction bed, then you might be lost. This is just one of the examples that I want to say about like how representative is the state that you are studying for the system. Another thing that is very important is in situ electron microscopy that we now use to study systems in a more relevant state has already quite important and developed history. This is an example from Hansen et al. In a science paper, and they have studied the same type of catalyst, copper on zinc oxide for methanol synthesis, and they looked at how the particles, the copper particles, adapt to changes in the gas phase at low pressures. So what you see here is after each time they change the gas phase, they just watched how the particle tries to reconfigure to minimize its energy configuration. And what you see is that different facets are exposed depending on the gas phase. So basically the particle or the system tried to find a low energy equilibrium state that is of benefit, yeah, for the system. And we learn a lot from that, but one difficulty here is that this is really equilibrium states, but the catalytic reaction is never running close to an equilibrium. It's a far away from equilibrium reaction, a catalytic reaction. And I just want to summarize this point a bit in this slide here. So what is an active catalyst? An active catalyst has to, of course, to break bonds and make new bonds. And if it's a good catalyst, he has to do that more than just once. So he has to do that over and over. So a catalytic cycle is going to run through many, many times until the catalyst deactivates. So there's some kind of a cyclic element in that. And as I said before, a catalyst, when it's active under reaction conditions, it is operated far away from thermodynamic equilibrium. That is obvious because you have a constant flow of adducts that come into your reactor, they react, and then they go. So it's an open system, things are coming and going. And then, of course, there's some heat exchange. So either you have to heat up your reactor or you have an exothermal reaction and heat is released. So there's heat exchange and mass exchange. It's an open system. Now, the funny or the beautiful thing is that under conditions where you have oscillatory or repetitive elements and you have an open system far away from thermodynamic equilibrium, something like dissipative structures can form. Dissipative structures are ordering phenomena that are only happening in such conditions. And in catalysis, this is known that such ordering phenomena can happen, dissipative structures, but they're only there under these conditions. You cannot study them when you're not under these non-equilibrium conditions. And that is why catalysts have to be studied under these non-equilibrium reactive conditions when they're really in their operational state. And of course, we have tried in the past and still try to make approximations. So we start with something that is close to equilibrium, you know, at low chemical potentials, and then we try to make approximation to the far from equilibrium state. But that is tricky because there are lots of non-linear processes involved and it's not a linear abstraction. So that's a bit difficult. Now I would like to show you some dissipative structures, and at the end of my talk, I come back to such structures. So what you see here on the right side is the famous Belousov-Zhabotinsky reaction. So you mix chemicals in a petri dish and it's a mixed state, but after some time, suddenly you see the appearance of these beautiful reaction fronts that are actually propagating like concentric circles, and often due to disturbances, they form spiral patterns. And when Belousov tried to publish this reaction, what he observed here, people were rejecting that paper and said, no, that's not possible. That contradicts the second law of thermodynamics. You cannot just suddenly create order from disorder. But then it was Zhabotinsky who explained it. He said that's a thermodynamic open system, and you can actually do this trick with entropy and create ordered structures. And this picture that you see here, that is taken by Ertel and co-workers. They studied CO oxidation on single crystal platinum surfaces with photoemission electron microscopy. So they are sensitive to changes in the work function due to different species on the surface. And what they saw is they saw reaction fronts moving, propagating outwards where adsorbates are reacted off and the work function changes. So this is beautiful dissipative structures. Now, if you turn off the reaction, they are gone and you cannot see them. And you would not know that they are there when they are under reaction. So this is the point that I want to make. You have to look at systems under reactive conditions. So now I have said this, and I also mentioned that you need to try to put things into some kind of a context embedded picture. What we have started to do when I was still in Berlin is we have modified slightly a conventional scanning electron microscope and environmental scanning electron microscope. And we use this to study macroscopic samples. Really, you can put in quite big samples in there, down to like the resolution limit of a few nanometers in that microscope. We can, due to some modification to the differential pumping setting, we did actually experiments up to 1 bar in that instrument. So we can bridge a quite large pressure range. You can see it here, for the base pressure is in the low 10 to the -4, 10 to the -5 Pascal, up to even like 1 bar. And we have a mass spectrometer connected, so we can do some reactions and then detect if something happens in the gas phase. So that is our, let's say, large scale instrument. And we combine this with transmission electron microscopy. And here at the ETH, we have a nice double aberration corrected grand arm. It's a special one because it is also, it can be used like an environmental TM, so we can actually introduce also directly gases into the column. And we combine this microscope with the climate system of dense solution. And with this, we can, of course, work up to 1 bar at the moment, maybe soon higher. And we can like operate up to 1000 degrees. And we have also a mass spectrometer connected to that system. And I would like to show you some simple examples of what we have studied with this combined multi-scale approach between SEM and TM. So we take simple systems that are somehow hopefully still understandable under catalytic relevant conditions, and we compare what we see in the SEM and what we see in the TM. I start with nickel. So, and I start with the SEM, and then I go to the TM. So what you see here is a movie that was recorded under in situ conditions in the SEM. You see on the top here, you see the time in minutes, so that it's running quite fast. The minutes are running here nearly like seconds. And what you see at the same time is here that something is happening. The contrast is getting dark, and after a while it's getting brighter. You see grains with different orientations. Some grains, we have analyzed their orientation. They are densely packed 111 oriented nickel grains. They are always in the dark state. Other grains, they are in a different orientation. They are a bit more nervous. They always flicker between bright and dark. Overall, however, there is a synchronization somehow. And we have looked at the surface, so I can tell you the bright state is a nickel oxide, and when it's dark, it's metallic nickel. And the system oscillates just because we have heated it to 600 degrees, and we introduced a constant flow of hydrogen and a constant flow of oxygen. So the atmosphere is constant, and the system starts to oscillate. And as it oscillates, we see that the consumption of hydrogen and oxygen starts to oscillate. We see that we form water that is also oscillating. And we see that when we form water, the system heats up and then it cools down again. And when it forms water, it heats up again. So this is a real thermocatalytic oscillation. So the temperature plays a role in the synchronization of this oscillating behavior. We know that when it's dark, that's the active state, we form water. When it's oxidized, it is the inactive state. So now, of course, we have the microscope, and that's the beauty about in situ electron microscopy. You are in control of all the parameters, and you see in real time the response of your system to stimuli. So what I just showed you this, we did lots of different types of testing parameters, but what you see here is we started with a constant flow of hydrogen. We didn't touch the hydrogen flow. So in a pure hydrogen atmosphere, it's difficult to form water. So we slowly introduced more and more oxygen. So this is the oxygen, like we start with 0.5 milliliter per minute, and so we increase the flow of oxygen. So once you have oxygen, hydrogen is already there. With oxygen, you start to form water. You're absolutely oxygen limited. So when you give a bit more oxygen, you form a bit more water. This goes up until a certain point, and the system starts to oscillate. That is very funny. So we form a bit more water. So we add a bit more oxygen, we form more water, and the oscillations change. At one point, we get like a period doubling and a bit higher. And at one point, I haven't plotted it here, but at one point, the system stays shorter and shorter times in the active phase where a lot of water is formed, and it goes more and more to the inactive state in which it's oxidic. And long before we were in the stoichiometric ratio, the system was inactive because it was just oxidized. So we found such a behavior where the water formation, the amount of water formed was at one point the maximum. Still oxygen limited for water formation, but that was the maximum we could get out of nickel at this temperature. And that point is exactly the point where the frequency that is plotted here, no, sorry, here is the period of the oscillations is plotted here. When we had the shortest period, so the fastest speed of these oscillations, that was when we had the highest activity. So when the system is actually right at the phase boundary between nickel and nickel oxide, and it's just flickering there, that's when we formed a lot of water. So the oscillations are somehow related with the catalytic behavior. We know in the metallic phase it's more active, in the oxidic phase it's not active, but the oscillations are happening due to the temperature that increase when you get reactive, and when it's dropping, when the reactivity stops, it goes back to the oxidic state. Now, as we have all these dynamics and we watch these dynamics, we were very interested in how these transitions happen between the oxidic and the metallic state. So we went through these oscillations, and in the transitions were very fast. So you see here, for example, the water is already falling down, and suddenly the brightness from dark, it goes very sharp up to bright because the system oxidizes. And this is really happening very fast. You see, this is one single frame in a scanning SEM image. And as we scan in this range, there's already an oxide on the surface, and in a single line on the other side of that scanning line, there is still the metal. So it's really within a single frame, the system flips from metallic to oxidic when the brightness goes up and the water is still dropping. So we looked at this transition between the nickel and the nickel oxide. So we can quench our experiment very fast. So we have nearly no inertia. We just quench the temperature down, and then we go to the FIB-SEM and we cut the FIB at the interface between metal and oxide. And when we look underneath the surface, we see beautifully that the transition, the oxidation from nickel to nickel oxide happens in a very orderly way. So you see here on the bottom, there's the nickel atoms or columns, and on top there are the planes of the nickel oxide. And it's really like a order transition plane by plane. That is a very fast process, and that's the reason why it can happen so fast actually. So it's an oxidation in the presence of hydrogen and oxygen when the system is oscillating. We looked at different orientations, so we saw also grains where the 1-1 planes of the nickel are at a different orientation compared to the ones of the nickel oxide. But again, you see this beautiful transition basically between the metal and the oxide. And it was nice to see that the earlier studies of Hayo Freund in Berlin under model conditions, under nearly UHV conditions, they studied the oxidation of nickel, and they saw similar order transitions and also tilted grain orientations. And that is beautiful because we have studied under conditions where water was formed, where hydrogen and oxygen were there simultaneously, but the elementary step of oxidation seems to be similar as if there was only oxygen. And when we looked at other systems, publication here from Eric Stark and colleagues, they looked at copper oxide interfaces, and they saw the same order transition from the metal to the oxide. I'll come back to copper later, that's why I showed this already here. So after looking at all this, we were still interested in understanding a bit what is the effect of the chemical potential and what drives the system really into these oscillations. And I show you here on the left and the right side two videos. Let's first start with the left one. This was recorded at the low pressure, so 10 to the minus 2 Pascal. And when I play this video, you will see that the metallic state spreads over only one grain, and then like the oxide starts to win over, and then the next wave of reduction happens, and then the oxide wins over again. And here, not the whole surface was infected by these oscillations, just like two grains. Other grains did not really bother, they stayed in the oxidic state. And on the other side, sorry, on the right side in this video, this was recorded at the higher pressure, so higher chemical potential. Here the oxidation is much more severe, and everything that is happening here is much more severe. You see the flickering because the temperature of the sample changes. There's so much water formation that we had instabilities. So this is something I want to point out. The effect of the chemical potential, the effect of the pressure is big. You have complete different behavior. The fundamentals are the same. You form an oxide and you reduce it, but the way how the oxide grows and all these dynamics are quite different. So after looking at this system for quite a while, we said, okay, let's look at this in the TEM. So we used the dense holder, we loaded it with nickel particles, and here's what we saw. You see, this is a nickel particle at 700 degrees. The cell is pressurized to 200 millibar. We have hydrogen and oxygen, and at the beginning, this particle is in the metallic state. And as I play the video, you will see that there's some kind of like redox dynamics on the surface. You see that there's some outgrowth of cubic nickel oxide happening, but overall it's in the metallic state. So this state here is actually similar to the metallic state in the SEM. This is the reactive state where we form water. But like in the SEM, after around 2 minutes of like flickering around, the system falls into the oxidic state, similar to the SEM. So now it's in the inactive state. It's reconfiguring. It's not completely happy either in the oxidic state because there's hydrogen around. And after a while, the system, the hydrogen wins over and it goes back to the metallic state that is happening now. And the funny thing is that these oscillations, they happen at like frequencies of like 1 oscillation per 2 minutes, more or less. And it was going on and on like this forever. And then we looked at the coupling. On the left side, you see a number of particles. Now this is metallic. This is now oxidic down here. You see they're flickering, but they're not synchronized. Yeah? This is, let's say this is now metallic. Now it's oxidic. But when they touch each other, it's like infecting, it's like a disease or something. The temperature, the contact plays a role, and this we can see on the right side, where the grains are all together in the foil, thermal contact is given. So when some guys get extremely active, they heat up because water formation is exothermal, the heat spreads, and they all get metallic and active. And then there's some mechanism that brings it back into deactivation, it cools down and it gets oxidic. Yeah, it's beautiful to watch, but I can still not understand everything, so this is still not published. We're looking at this system since many years. Let's switch to something else then. I have another simple system, copper. Copper has been studied a lot and is still studied a lot. It's an important catalyst for many reactions in this industrial chemistry. And so we started again first in the SEM to just study copper. How does copper behave when you offer it oxygen, for example? Yeah, we started with just pure oxidation to learn a bit more about copper. And what the video that you see here is low chemical potentials, low pressure of oxygen, and very slow surface oxidation. You see oxide islands growing on the metallic copper. It's beautiful. Actually, when you look at this, you see there's like a wave-like structure at the front of the oxidation front. The video is really sped up. What you have seen here is actually 2.6 hours. It's a very slow oxidation process, and we looked at these details, and we took many videos. I'll show you another one. This is different grains. You see some grains are only surface reconstructed because of the oxygen. In other grains, the oxide is really growing. You see here the step flow grows, like in the TM observation, but here macroscopic. So it's beautiful how the things are fitting together. And you can already see here that different grains behave differently. And you can learn quite a lot just from such beautiful videos. Each time I watch it, I get excited. So then, after looking how copper oxidizes at different pressure, different temperatures, and so on, we said, okay, let's do the chemistry game. Let's do redox reaction. Very simple, and the most elementary redox reaction is hydrogen with oxygen. So now we know how oxidation looks like. Let's add hydrogen and let's do the game. And this is how it looks like. So the time is running here. You see, because of the action of oxygen, there are oxide islands forming. But once the oxide has formed, the hydrogen can kick in and start the reduction process. And the beautiful thing in this video is you can look at the video and you can look at the boundaries where oxide is reduced by hydrogen, and you know where water is forming. So you can look at the movie and you can tell water forms here, where the oxide islands is getting eaten off. And we were, of course, wondering, is there some other places where catalytic water formation happens? Not just water formation from reduction of oxide, but maybe some water formation by some other catalytic mechanism. So first we needed to see, do we really form water? Yes, we do. So as we ramp up the temperature in this reaction feed at a certain temperature, I mean, it's not a very beautiful mass spectrum, I must say, but you see water signal goes up because some desorption when you heat up a surface. But at around 400 degrees, we saw that the water formation really rises. So we could see once the dynamics kick in, we also form water. So these dynamics are related to water formation. So then we mapped, a PhD student of mine, mapped the whole parameter space, ratios of hydrogen to oxygen and different temperatures. And in this whole mapping, we found a quite nice, intriguing regime. And this is in this video. You see there are like waves propagating across the surface. I have indicated this with color. So there's a one wave where you see a reconstructed surface. Then there's a wave that flattens the surface. And then on the flat surface, there are the oxide islands propagating. The interesting thing is the oxide islands are only propagating into the flat state. And after the flat state, when the oxide has removed again, you form this reconstructed state. So we identified 3 different morphologies on the surface: the stepped, the flat, and the oxide, and they were like one after the other, and sometimes the waves could even propagate across grain boundaries and so on. You would have to watch this video maybe for hours to see all the details. There's quite a lot of things happening here. But So we studied this and we wanted to know what is really going on. So we took single crystals of copper and we did the same process. And this is a copper 110 crystal. And there are some oxide islands growing randomly, but some are really defined going in a specific direction. And what you see here is a spike of oxide growing downwards. It grows downwards, but it also grows sidewards. And as it grows sidewards here, because there's hydrogen also, the oxide is not long living. So the oxide grows sidewards, but in the center, it already starts to reduce. And you see when it grows sidewards, you see there's like a bow wave, like in a boat on the left and right side. You see that better in the next slide. And we looked at this and we said, okay, let's quench the system. Let's take a region and do a Fib cut through that. So the dark thing, that's the oxide. It grows sidewards. So this is a growth from to that direction. That's a growth from to this direction. And in the middle, there's already reduction. And when I look at this Fib lamella here, you see this is the oxide that was growing in this direction, pushing the copper a bit. So you form this bow wave that we see even here. And we saw it in the previous video. The oxide that forms is not stable forever. It gets reduced. Here is already reduction happening in the middle. But the interesting thing, we saw that before reduction, the oxide is also changing a bit. It develops specific facets here before reduction. This is the same to the right side here. Of course, when we have a Fib lamella, we can go to the TEM, and we studied then in detail. We wanted to see along which directions does the oxide grow, how does the growth happen, the growth of the oxide proceed towards the bulk. We try to understand which facets are forming when the oxide is getting reduced. There are lots of details in here. And after all of these studies, we figured out, okay, that is a sequence of steps that are happening. And I show you quickly the model of what is happening. So the oxygen can induce surface reconstructions. There are some very stable surface reconstructions induced by oxygen. They can preserve quite long. And it takes some time until this oxygen reconstruction is lifted by even more oxygen on the surface. Then you get it in this flat state. This flat state is quite interesting. That's the precursor phase to oxide growth. And on this flat state, there's lots of oxygen. You can actually grow an oxide, but there's hydrogen constantly feeding from there. So here you form water. But anyhow, the oxygen wins and you form an oxide island. That's here. But hydrogen wants to reduce, and here in the reduction of the oxide, you also form water. So you have two ways where you form water, and it's beautiful because we can look at the time constants. We get a bit of a rate barriers and stuff from this observation. Now, let's go to the TM and see how that looks like in the TM. We have copper in hydrogen, oxygen at some temperature, and off we go. You see these particles are quite dynamic. There's lots of movements going on. Particles are sintering. And then if you look at this particle, for example, they're not only sintering, there's also something happening. They can also split to parts. So there's quite some interesting dynamic that leads to the stabilization of a certain size regime depending on the conditions. This is a bright field TM. You see a sintering process, but what you also see is that the particles of copper, because of the oxygen, they form copper oxide outgrowth. So they grow like noses or tails of copper oxide. In a microscope, of course, we can analyze what kinds of phases there are involved. So we do electron diffraction. We integrate the electron diffraction pattern over time. We analyze the intensity of the rings. And we know more or less quantitatively how much copper and copper oxide phases there are. We always only found metallic copper, copper 1+, these two phases. In the TM images, we saw usually beautiful crystalline transitions between the metal and the metal oxide. In general, in my videos, you will always see that I try to not take high resolution, because as soon as we go too close with too many electrons, and then we have beam issues. So most of the dynamics I'll look at from a safe distance. Anyhow, we wanted to check if all these dynamics are related to catalytic water formation. So we have a mass spectrometer connected to our setup. And here's what we get when we have this tiny amount of catalyst between these MEMS chips in the microscope. And we study the dynamics. And at the same time, we see when we ramp up the temperature, when do the dynamics set in, and is there any water forming? And you see here, don't really look at the oxygen and the water signal. It's not extremely beautiful with some background issues. When you heat up every surface, there's some water desorption, but at around some temperature, the water formation goes up. More trustable is the oxygen signal. So the oxygen signal, we can see there is no consumption of oxygen up to around 400 degrees, similar to the ESM, the SEM videos that I showed you before. At around 400 degrees, you see that the consumption of oxygen starts to happen, and you consume, in this case, oxygen by hydrogen, you form water. And just to test if this is really only the copper, we assembled an empty cell of these MEMS chips, and we did the same thing. So we heated up, there's again some water desorption from the walls, but no oxygen is consumed all the way. So when there is no catalyst, hydrogen and oxygen do not react, even up to like 800 degrees or so. There is no self-ignition and so on at these pressures and at these ratios that we used here. So clearly what we see, this dynamics, as soon as the dynamics kick in, we see water. So that was quite nice. And I want to say something about particle size distributions. In catalysis, when you do electron microscopy in catalysis, you will often be asked by people to analyze their sample for size distributions. We have observed so many systems, and it's beautiful how actually the particles don't care about how big you synthesize them, but the reaction conditions, they define how big particles will be under reactive conditions. So let me show you this video here on the left side. I think first the right one starts. Try to ignore the right one. Look at the left one. So this is copper particles, first in hydrogen helium, and we slowly introduce oxygen. And as oxygen comes in, then this redox dynamics start to pull and push, and the particle, they fall to dust. It's like metal dusting. You see lots of small particles are forming here. The interesting thing is they don't just fall to smaller and smaller and smaller particles until you just have clusters of copper. There's a certain size regime that is stabilizing. Now let's switch to the left video. I have to go back to start here. What we did here is we started with a hydrogen-oxygen mixture. So it's already redox conditions, but at the beginning, hydrogen is leading. So you have mostly metallic, roundish shaped particles. There's some oxide outgrowth on some particles because there's oxygen also there. But as the video plays, we increased slowly the amount of oxygen, so the oxidizing force in the game of the two gets stronger. And you see that there's some oxide tails and stuff, but more and more oxygen comes in, so these oxide tails get a bit more dominant with the video going. I also see that the bigger particles have now fallen into pieces. You see more smaller particles, and you see amazing dynamics. The time is running here. This is seconds, so it's really, really fast dynamics. These particles are like moving like living things on these silicon nitride membranes here. So a lot of dynamics, and the size really is defined by the reaction conditions. So we have looked at quite a few systems, and they were all showing interesting dynamics. I just want to show that we did not only study the formation of water, which is maybe not interesting for catalysis, but it's a good elementary redox reaction. But we went on and studied copper in methanol oxidation. And we have a lot of data. Just show you one video that is like someone told me once that's chemical pornography. What you see here is just crazy, that this copper is not even, it looks like a liquid. Some particles were enclosed because we had some contamination issues, but those particles that are really exposed to the methanol, they were doing quite amazing things. So it's extremely dynamic. And we have also looked at palladium in methane oxidation. That is a video from this reaction. So this palladium particles. And you see that also the palladium does some redox chemistry here with the gas phase and also itself. So the palladium particles, they form outgrowth here, this bubbling out palladium oxide. It's not stable for long. It forms again palladium particles. And here again, with our MEMS chips assembled, connected to the mass spectrometer, this reaction was a bit more friendly but higher conversion. We could clearly see when we are in the active regime and we basically burn methane, the catalyst was quite dynamic. And when we go to the lower temperature, where the consumption stops, no more CO2 is formed, everything was basically frozen. Yeah. And then we studied platinum and hydrogen oxidation, don't show that now. And also very interesting silver in methanol oxidation. Silver is volatile, and there were lots of amazing things going on. And again, a reaction where the size really depends on the operation conditions. So you think you have a certain size regime, you cool down, and during cooling already the size regime changes. So catalysts need to be studied under reactive conditions, otherwise you end up with wrong numbers. So I want to conclude a bit this part. So as I said already, the active catalysts that we have looked at, they were all dynamic under reaction conditions. And you can imagine, we know this from physics, quantum physics and wherever, there is no interaction-free interaction. On the atomic scale, if something else comes and there's some charge moving, there is always something happening. So active catalysts are dynamic. And what we need to do is we need to design catalysts that allow us to stabilize these relevant dynamics. That's the art of catalysis development, to stabilize the relevant dynamic state. And one thing that is wrong is you cannot synthesize a catalyst. What you synthesize is a precursor. Under reaction conditions, the reaction environment transforms the precursor to an active state, but you cannot say, I designed this catalyst or I synthesized this catalyst. That would just be wrong. So as I say here, the precursor turns into the active catalyst in the interaction with the reaction feed. So the reaction conditions are also relevant. So if some people use one stoichiometric ratio for any conditions, but depending on the pressure and temperature, you need to adapt. And as I said already, catalysts need to be studied under reactive conditions. That's very important. And because it's so complex about so many scales, we need to do a bridging of scales. So we have to make sure that we consider the pressure gaps. Things at low pressure are different to things at high pressure, as I tried to show. There's a material gaps in terms of complexity. Now we started with simple single metals or foils and particles, but the next thing is to do supported catalyst and. So, and altogether we need a multi-scale approach, like not only electron microscopy, which is local, but we have to combine it with some in situ spectroscopic integral methods, like things that you find in the beamline. So altogether it should really go hand in hand, and the TM community and electron microscopy community should really move closer to the spectroscopic community. Before I stop, I have one more story. We did some growth of graphene and different substrates and different metals in the scanning electron microscope. So we start with a polycrystalline platinum, we put it in the chamber and we anneal it at 900 degrees or so. And then you see the surface cleans up, recrystallizes, gets beautiful. And then once we think it's clean, we take one grain, zoom in, and then we introduce a carbon source and hydrogen here at 900 degrees. So imagine you have a hot surface glowing, emitting thermal electrons, and now we want to see single layer graphene forming. And it's possible. We were stunned when we saw that. So when we introduce ethylene and hydrogen, you see the nucleation of graphene islands, they merge, coalescence to a film, and we can observe that in real time. We also see here that somewhere from the contrast, you see that there's a second layer forming here. We see here there's multi-layer graphene forming. We can really count from the contrast how many layers we have. So in an SCM, even at 1000 degrees, you don't have lateral resolution like an atomic scale, but I can count atomic layers that grow towards me. So I have some kind of atomic resolution. And then we did growth dynamic studies. We looked at coalescence behavior between graphene islands. And as we see the propagation of the growth fronts, and for example, how these different islands nucleate together and how a concave angle between them turns into a convex angle, just by looking at the dynamics, that's an additional information about the system. We could reconstruct atomistic details of what happens at the growth front when a concave angle actually roundens up and turns into a convex angle here. So the SCM is really amazingly sensitive. And with this, a friend came to me and he asked me, Mark, I looked with my field ion microscope and field electron microscope and some beautiful and important reaction, NO2 hydrogenation. So he has a tip, he absorbs NO2 and he reacts it with hydrogen. When NO2 is on the tip, the work function is high, it's dark. But then at one point, hydrogen reacts it off and he gets a spike of brightness. So he got an oscillating reaction and he asked, can we see the absorption of NO2 in SCM and do this reaction? So we tried. We cleaned the surface for a long time, it's platinum. We introduced NO2 just to see if the work function changes when we introduce NO2. And it got dark. There could be contamination, could be anything, but we cleaned the sample for like 2 months in the SCM. And afterwards, when we heat up, whatever has absorbed seems to desorb again. Let's try it now. Let's do the reaction. So we have here a polycrystalline platinum foil. We introduced NO2 first, and then as the video will run, you see that we introduce hydrogen. You don't see the hydrogen, but we introduce hydrogen, and the hydrogen starts to react off on some grains. This will happen now. So I introduce hydrogen, and then you see cleans off. Then due to impatience, some overspiking, and then we regulate it back down. And now you see what I mentioned at the beginning, beautiful spiral patterns, dissipative structures. So what you see here in the SCM is the propagation of reaction fronts when species of NO2 adsorb on the surface and react with hydrogen. Now we did some contrast treatment, so we removed the contrast due to different grain orientations, channeling contrast and work function contrast. And now I show you a video that is just having contrast due to the adsorbed species on the surface. Meanwhile, we know what is on the surface, like Erdl already suggested, that you form a platinum surface oxide. And this is reacted off with hydrogen. And you see the different grains. Some are still covered, some are immediately lifting off, some are beautifully reactive. Reaction fronts can work themselves into still so far unreactive areas. There are chemical clocks that initiate the reaction. And you see, for example, here, reaction fronts propagating downwards. Something here acts as a chemical clock. But as soon as this guy connects, this has a different frequency and acts as a chemical clock upwards. Beautiful spiral pattern and reaction fronts. And we can, of course, analyze with EBSD the orientation of the grains. We can tell this orientation is so active, that is more active, and so on. And we can also see how this reaction really happens. So we see when it's dark, it's covered with adsorbed NO2 basically, and when it's getting bright, it is when it's reacted off. And once it's reacted off, it starts to adsorb until a certain level, and then it reacts off again. So it's an excitable system that builds up some kind of like coverage until it excites again. So we see this sawtooth behavior. We can see how long this recovery time takes until the next launch can happen, depending on the grain orientation, on the catalytic properties of a specific grain. And we beautifully see that this threshold behavior, that's an excitable system. So you have to build up a potential, and then you can react off, and all these times of building off. And so we can see it's like a toilet as an excitable system. So you can like flush the toilet. That's when you de-excite. And then the filling of the water reservoir is the time that it takes until the system can be re-excited. And lots of systems are excitable. A forest fire that burns down and then the trees regrow, it's an excitable system. Or here is a fungus species here, and this is the Belusa-Saputinsky reaction. And these, I come back to this point, these are dissipative structures, and you cannot see them when you're not there, when you're not under these far away from equilibrium conditions, where you have an oscillating element embedded. And that is what is often in catalysis. So Erdl showed that in the photo emission electron microscope. People have shown oscillating reactions also in the field emission electron microscope. And the SCM is actually as sensitive as a PEM, but we can actually operate in a quite large range of pressures. And this is thing that I think is quite beautifully showing how beautiful chemistry is when it is at work, and what we would miss if we would not do in situ. Is this thing I would actually end here. I want to first thank my co-workers, my former PhD students that have now already a PhD, and guests and new PhD students and colleagues that have been involved also with these NO2 hydrogenation reactions. My TM colleagues, some went with me to ETH Zürich, some are married, and then new colleagues, Professor Schlögl, who was supporting me at the time at the Fritz Haber Institute. And I want to thank you for your attention.
All right, Mark, and we want to thank you for your great presentation. So
thank you.
Thank you very much. And now we will have some time for a Q&A. First, we will have 2 questions of our product manager, and then we will get to the questions of our attendees. So Ronald, please go ahead.
Yes, thank you very much. Also, thank you, Mark, for this very exciting presentation. Lots of dynamic stuff of all these nanoparticles moving around the screen. And you even took us to the world of what you call chemical pornography, and down to the flushing of the toilets.
Yes,
but it was really an exciting journey. I think you are one of the best people to explain about what you can do in the field of catalysis with in situ gas and heating. You've also been using climate system for more than 4 years, since early 2016, and you've seen all the different versions of nanoreactors that we have produced over the years, starting with the first FEI climate nanoreactor, and then when you moved to Zurich, you went to work on a jail with a jail nanoreactor, and lately you started using the EDS compatible nanoreactor. Mm-hmm. So I want to ask you, given all your experience with these different models, what type of nanoreactor do you like most for using with catalysis in situ experiment?
I mean, the development was impressive. So each new generation was better than the previous one. So I remember discussions about like the temperature homogeneity and like issues with drift and bulging and so on. And it got better and better and better. Now with the added ability to do EDX, of course, that's great. So we can see we have all these dynamics, but we also want to know what is moving here, and now we can couple that with EDX. Yeah, as I think I already said earlier, it's amazing, and I'm looking forward what will be happening in the next 5 years if the progress continues like this. Like if customers give feedback and maybe if you find things that should still be improved, or so it's an amazing field to be in at the moment. This whole in situ thing with the tools that are getting better and better and more versatile, and with EDX capabilities, and especially with our microscope, we have two huge EDX detectors. We can really get a nice signal.
Okay, yeah, thank you for that. And then I have a second question. Mm-hmm. This is more in the field of the software development. So yeah, we started out with DigiHeater software to control the heating function, and then back in Berlin you had your own gas system to control the gas flow. And yeah, more recently we introduced Impulse for combined gas and heating, and also using the same API, we together with Catan had a plugin for Catan digital micrograph, where you can control gas and heating experiments. You've been one of the first users for that plugin. Can you tell us a little bit about your experience with that digital micrograph plugin?
Yeah, so I mean, as a human with only 2 hands, you're quite limited when you do in situ experiments, especially at the beginning. Now we had to get up sometimes, you know, change our gas valve on somewhere on our boom, and then you have to control the microscope, and you get so excited. But then someone should actually make some notes about what are the conditions now, which temperature. So it was basically we had to be 2 or 3 people at the microscope at each moment. But now we have this nice software integration. I hear some echo. Interesting. I continue. So we have everything now nicely integrated. So we sit at the computer, we record our videos, and all the data is recorded simultaneously. And when I play the data afterwards, I see things happening in the video, and I see at the same time the plot of the gas phase composition, how that changed, and I see the temperature, how that was followed in each frame. So it's like, yeah, it's turning more towards a single person job. So it's getting more doable to keep track of everything that is happening. So I'm really happy that we have this. Also later on, when you have all the data to try to put together, you know, it's with this and that picture, that's crazy. And now it's much better. I'm happy.
All right. Yeah, thank you very much for your comments, Mark.
Welcome.
And back to Olaf now.
Yes, and also to the attendees, please keep posting your questions. We will now answer a few of them. And for the first question, I want to give the floor to Yuan from Yukon. Are you there? Yes?
Yes, this is Yuan Yuan. Hi, this is Yuan Yuan Zhu from University of Connecticut. Hi, Mark.
Hello, hi. Nice to see you. I hear you.
Yeah. Thank you for the fantastic talk. So actually, I posted a general question, but I think maybe I can ask a more specific question. So it was fantastic to see that your operando data being able to actually pinpoint, right, the highest conversion of water is at this transition state of between the metallic phase and oxide phase. So do you think it's possible to stabilize that transition phase? But if oscillation is the nature of this reaction, it's kind of how to say counterproductive to try to even stabilize it. So how do you think this oscillatory state can really help perhaps to design better catalysts?
Yeah, that's a very good question. People have asked that, and people have tried that even in the past, to use oscillatory reactions and influence them to try to work against it. So what I did in the SEM, I tried to counteract with a heater to keep it in that regime. But the point is that, like, I heated the foil in the SCM, and the reaction happens on the surface, and until the temperature propagated to my sensor, it was already, so I couldn't follow it. So, but yes, I think that is something that is still very challenging. So the oscillations that we had were the minutes regime, and the activity, the catalyst, there's things wiggling around at much faster speeds.
Yeah.
But the system reacts on it, and it falls out of this regime. If you could stabilize that somehow, that would be great. But we found that the activity was always close to a phase boundary of a system, at the point where the nickel is not hesitating to take oxygen and give it away. Yeah. So it's always close to the phase boundary. You can put some promoters to, like, spread the phase boundary a bit and make it more accessible. You can. I mean, this is a wonderful field. I would love to do more in this direction. I think it's very exciting to try to stabilize these relevant dynamics.
Right, and especially as you mentioned, as synthesized, the catalyst is like in the precursor state, right?
Absolutely.
It is still a huge gap, I think, that between the precursor, which we can really characterize down to atomic detail, but then you have this dynamic, really working catalyst, and how to bridge that perhaps is another question, right? To trying to stabilize.
Absolutely. You see how many papers are published or people say we synthesized this and that catalyst, claiming things. But I was leading a microscopic group for catalysis for many years. We looked at thousands of catalysts, and the thing before and after, there are some catalysts that seem to not change much, yeah, but they have some secrets of operation that I don't know yet. But yes, it's true. You cannot really, you need to study catalysts under relevant conditions, and that would have, I mean, not enough people are doing that yet. It would have a bigger impact if we would speak more with the companies, and it's still a bit just too few people doing that, I think.
I agree. Okay, thank you. I'll let other people.
Thank you very much.
Thank you, Mark.
Thank you.
All right, thank you for that question. And the next question is from Lang Kin from the Ohio State University.
Yeah, hi, Mark.
Hello, hi.
Yeah, this is Lang. It's great talk. I'm not really working in catalysis. I work in chemical looping, which is a process, kind of a indirect catalyst process. So I'm more care about the final gaseous product. So I'm just wondering if the in-situ TEM, like through the detection, you can not only detect the solid evolution, but what about the gas product or reactant?
Yes. So we did this, for example, with calcium oxide to carbon dioxide uptake to calcium carbonate and the CO2 release and such things. You can, the MS, if you have a sufficient amount of sampling there, you can easily detect what comes out in the gas phase when you do some chemical looping reactions. It always depends, of course, you have tiny amounts of sample in your catalyst, but yes, it is possible, maybe not for all systems, but you can study chemical looping nicely with such things. What I didn't talk much about is like the influence of the electron beam. Like if you have some very sensitive materials that are not stable under the electron beam, then maybe electron microscopy is not the method of choice. This is always one thing you have to consider in these experiments. But in principle, there I don't see any other obstacle to study against studying chemical looping, if this was your question.
Yeah, that was the question. And I also wonder what reducing gases, do you have any limitations for the gas choice?
I really love Professor Schlögl, because he said if mankind needs this experiment, we do it, even if the microscope is broken in the end. So it depends on your budget. But we have worked with ammonia. We had introduced ozone, and we were not extremely gentle. So maybe there are some gases that then solution specifies that you're allowed to do. Then there are some security regulations normally.
Just wondering if H2S is too extreme.
Sorry?
If H2S is too extreme.
Yeah, I don't really know how it depends on the concentration and on the security measures, and then maybe for the materials you need to ask then solutions. You don't want that the window breaks, for example, in your experiment when you work with such gases. Yeah, but I don't want to give advice and then something bad happens in with such specific gas types.
Yeah, thanks. Thank you.
You're welcome. Welcome. Good luck.
All right. Thank you very much. Then the next question is from Chao Ying from the University of Delaware.
Hi, good afternoon. Thank you very much for the talk, Mark. It's very good. This is Chao Ying from University of Delaware. I have a question basically based on the definition of catalyst, and it does not, sort of like it does participate in reaction, but will not be consumed. Now, my question is, did you actually check the mass spec of the gas? Did you see the actual catalytic metal phase?
This is also a good question. I mean, yes, the catalyst shouldn't be consumed, and when we have oscillatory behavior, it comes back. But we studied systems where parts were quite volatile. Yeah, and there are actually theories according to which the catalytic reaction actually doesn't happen on the surface of a metal, for example, but there is some kind of a vapor phase just on top, and there something goes on. We're looking at that. So some species are quite volatile, and I have some videos where you can see things disappear and redepositing somewhere else. In the catalyst, we know that if you have a bed, you actually lose some of it on one side and you enrich on the other side. So there is transport through the gas phase also happening, and that is a way of deactivating because you lose active catalyst by streaming it to the exhaust. In the reactions that I showed it today, we didn't study that, but we have examples where we looking at this because it's quite interesting, and I blame quite a bit of the reaction happens in the gas phase on top of the metal. But this is something I'm not yet sure enough to really tell something. But yeah,
it's pretty dramatic on my mind. It's thank you very much.
Thank you for your interest.
Thank you.
Okay, so thank you very much. And the next question is from Thomas Willem Hansen.
Hey, Mark, how are you doing?
I'm fine. Nice to hear you, Thomas.
Likewise. All of your images, they did not seem to contain any information about electron dose rates. Now, for quite some time now, we've known that the beam has a significant influence on these structures. And there's been a lot of effort, and also the novel cameras, you can go really low in dose rate, and you can do nice things at extremely low dose rates. So what kind of observations have you done of the electron beam in the closed cell systems?
This is a very important question, and we should make a webinar just on this topic because it really deserves all attention. So it is really funny because I don't know, I'm a physicist and I don't understand very complex. I always try to do things simple. So we started with hydrogen and oxygen. The electron beam shifts the chemical balance a bit between the two. They can make radicals. In the case of oxygen, you can shift the chemical potential a bit more towards the, if you activate the oxygen, it gets more oxidized, and if you activate the hydrogen, it gets a bit more reducing. So what we saw in these experiments is when we increase the intensity and focus the beam, at one point you start to see really the effect of the beam. That is obvious. So for example, in these reactions, the beam actually shifted the potential towards more reducing. So we, at one point, when you focus the beam to a particle, it starts to stop doing this redox. It stays, it's frozen in the metallic state. But then we saw, okay, now we have actually increased the reducing conditions with the beam. Then we could actually counteract and turn up a bit the oxygen chemical potential, and we brought the particle back into this flickering state. And then when we opened the beam, the oxygen was, of course, winning. So we could actually, in this very simple system, that's why I like to start simple systems, you can shift and compensate a bit the electron beam. Of course, we try, and you didn't see many high-resolution videos because we know that as soon as I show you these dynamics, if I zoom in, have more beam intensity, then we get artifacts that I can correct with some. I mean, beams don't create unicorns, right? They just shift the chemical balance a bit. If you have complex molecules, of course, it gets complicated, but with hydrogen and oxygen, it's still simple. With methanol oxidation and copper, the beam was much more complicated, and we had to spread, and I only show you overview dynamics. And I'm also here counting on future detectors that are extremely efficient. Each electron counts, and we can spread the beam further, but we will always be in a dilemma. You know, the dynamics are fast, we need to take many pictures, we need to do it ideally without electron. So that's a topic, and we should discuss this in more detail, definitely.
I completely agree.
Thank you.
Okay, well, thank you very much for your question, Thomas, and for your answer. Another question was from Raval Dunin-Borkowski. Raval, are you there?
I think so. Can you hear me, Mark?
Yeah,
yes,
we can hear you.
Wonderful, Rafael. Nice to hear from you.
So, Mark, sometimes we hear about catalytic reactions being affected by an external magnetic field. Does the 2 Tesla magnetic field of the microscope objective lens ever affect catalytic reactions?
I have never seen any effect of the magnetic fields in the systems that we have studied. So we had, for example, the magnetic nickel particles in there, and we saw random stuff. We didn't see anything that is very different to what we saw in the SCM, where the magnetic field is lower. It is an interesting question, but you would need to see if any orbitals are polarizable. I don't want to see something that is stupid. I'm not deep enough expert into that. But in the general overview about the catalysis, there are not so many cases where I heard about the use of magnetic fields. But of course, the beauty is that we have, of course, also control of magnetic fields in the electron microscope. I mean, it's conflict sometimes with imaging, but we could at least detect local magnetic fields. But I have never looked into that. I think it's worth to think about this more.
And nowadays you can do atomic resolution imaging in zero field conditions as well as in the presence of a field, so it's possible to do comparisons.
Absolutely, that would be great. I read about this development of a zero field objective lens, and I would definitely be interested to try that.
Okay, thank you.
Thank you.
So with this, I want to close off and thank big thanks to Mark, of course.
Yeah, thank you everyone for listening, and thank you very much for hosting me.
Yeah, and we hope to see you soon with another webinar, because I think you still have a lot to share. So
I should first write up a few things, but yeah, we have quite a few things lying around.
Yeah. Ronald, closing words?
Well, thank you all very much. First of all, thank you, Mark, for your presentation. Also, thank you, Olaf, for putting this all together. And I think I'll leave it with that. Okay, goodbye.
Okay, thank you, everyone. Goodbye.
Okay, and with that, we come to the end of this Nanotalk. Thank you all for watching, and I invite you to follow us on our social media accounts, LinkedIn and Twitter foremostly, and also subscribe to our newsletter so you will always be informed if we will organize new webinars. And well, this was it. Thank you for watching and see you soon.